Hello, this is your physics TA Landon, and today we'll be looking at exercises 7 and 10 from chapter 2. That will be found on page 3, and by 3 I mean page 34 and page 35 of Don't Panic. Okay, so let's get started. A lot of you had some smaller questions, more specific ones. However, hopefully we'll address all of these questions as we go through these problems rather than address one at a time. Okay? So, go ahead and read the problem if you're not familiar with it. This is exercise 7. We have a rocket which is starting at the top of a building and being fired straight down towards the ground. We are told the acceleration towards the ground is equal to beta times t, where beta is a known constant. Okay? We want to know how long it takes for the rocket to hit the ground and how fast it will be going when it hits the ground as well. Okay? So, the first thing we need is, well, we sketched it. We need a coordinate system to describe where this rocket is located over time. Okay? And the reason why is because that coordinate system is going to help us get this physical distance h involved. So we know the distance from the ground to the top of the building is h. Alright, so let's choose a coordinate system. Alright, where we have the origin up at the top where the rocket starts, so the rocket's starting there. We're going to make not only our time origin there, so t equals 0 there, but also our space origin there. X is going to be equal to 0. And we'll have x increasing as we go down towards the ground. So this is x equal to 0. Alright? Now, because we chose our positive x direction to be down, right, we have increasing distances down here, right? For example, we had 1 meter, 2 meter, 3 meters, right? But that's not important. None of those points are important. All that matters is this next distance h, okay? So, what if you made a coordinate system so that 0 was the coordinate for the ground, okay? Well, in that situation, if you chose the increasing values to be up, so if this were the positive x direction, right, then here we would have h up here. Okay, so your initial position would be h. Now the difference would be is this acceleration function, right, would be a little bit different. If beta is a constant greater than 0, we would have to write our acceleration function as negative beta t for that coordinate system, right? But no matter what our choice of coordinate system is, the velocity at the bottom should be the same either way. And the time it takes for the rocket to hit the ground should be the same. So we're just going to choose this first coordinate system on the left. But feel free to go ahead and solve the problem with the second coordinate system, and you'll show that the velocity is the same in both cases. Alright. So, do we know any information? Is there any other information I can write? For example, initial conditions. What's the velocity at time t equal to 0? Right? And that's going to be equal to 0 because we start at rest. What's the position at time t equal to 0? Well, that is going to depend on your coordinate system. And for our coordinate system, we chose 0 to be at the top. So x is 0 at time t equal to 0 when this rocket starts accelerating downwards. Now, here's another thing about coordinate systems, right? Why is it that I have 0 up at the top and not at the bottom? Well, think about a ruler, right? You have the 0 mark on a ruler. You can put that ruler in any orientation, or you can flip it around. You can put the 0 mark wherever you like, and it's still going to function as something that measures distances, right? The coordinate system you can think of the same way, right? It doesn't really matter where the 0 mark is. It's still going to function as something that tracks the position of the particle over time, or in this situation, a rocket. So you have the freedom to put the increasing direction wherever you want and have that 0 point start wherever you want. Now, granted, some coordinate choices are more convenient than the other. For example, if I want to measure this cell phone's length here, I would put the 0 mark of the ruler at one end of the cell phone to easily measure this length. And just read off the length right off the ruler, where the other edge of the cell phone meets the closest tick mark. So, for a coordinate system, right, it's the same way. I mean, I could put the 0 right for this ruler where I'm measuring the cell phone, like over to the right somewhere, and I could still measure this distance, the length of the cell phone to be whatever it is. And the thing is that distance is independent of where I have that 0 point for that ruler. So it's the same with coordinate systems, right? In physics, we're interested in changes in distance or changes in basically anything. We'll see later on we're interested in changes in energy, for example, not necessarily the absolute value of energy. So because we're measuring changes in physics, the origin of coordinate systems really doesn't matter. Okay, so proceeding. How do we find the velocity when the rocket hits the ground? Well, we need the velocity function, which is given by integrating the acceleration function. That's our general law. Okay, and that's integrating beta t. Integrating beta t gives us 1/2 beta t squared plus a constant. And we should get used to this by now. This constant's going to be the initial velocity for the velocity function, right? How do we prove that? Well, let's just go ahead and write that constant as a c here, and then evaluate it at t equal to 0. So I'm just proving that that constant is the initial velocity. So I'll plug in a 0 when I see a t. This is 0. So reading from right to left, I get c is equal to v evaluated at 0. And that's the proof. Okay? So writing the velocity function, 1/2 beta t squared. Now c as the velocity at t equal to 0. The rocket starts at rest. Right? So at this point in any problem, we're going to go back to our description and see if we know the velocity at time t equal to 0. In this case, we know it's 0. Alright, so now can I find the velocity at the time whenever the rocket hits the ground? Yeah, we can if we know the time it takes for the rocket to hit the ground. Unfortunately, we're not given that information, so we need to find that information. So what physically haven't we put into this problem yet? Well, we just have the acceleration and the velocity function. We did not incorporate the fact that the rocket travels a distance h yet in the amount of time it takes to reach the ground. So in order to do that, we need the position function. The position function is given by integrating, the position function, x of t, is given by integrating v of t, and we get 1/6 beta t cubed because we integrate 1/2 beta t squared. If you're not sure of that, please take some time to review that integration. And the integration here is going to be this function x evaluated at 0. The constant of integration. Looking at our coordinate system will tell us what x is at time t equal to 0. And, well, it's 0. Okay? So we go ahead and cross this out and put a 0. Okay, so what was I saying earlier about, well, we need to incorporate the fact that this rocket travels a distance h? Well, here's what I mean. Okay, first, let t, although we don't know it, we can still define a letter to represent this. Let t, capital T, be the time when the rocket hits the ground. Okay. So I look at my picture. Where's my picture? It's up here. And I say, okay, when the rocket hits the ground, it's at a coordinate x equal to h. So if I have x as a function of time, which I do, I take that function, I evaluate it at the time the rocket hits the ground, I should get h. Okay, so let's go ahead and evaluate x at that time and set it equal to h. So x is equal to 1/6 beta t cubed. This function is very powerful. It gives me the coordinate of the rocket at any time t because I know what beta is. And I can just plug in 1 second, 2 seconds, 3 seconds for t, whatever, and that'll give me where it is. So I kind of know a lot already. But now I want to evaluate this function at the specific time t cubed, which is when it hits the ground. I don't know that time. I can still put an unknown in an equation, though. I have the power to do that. I do know h and I do know beta, so I can now solve this equation for the time it takes for the rocket to hit the ground. And if you're not comfortable with this algebra, please prove this yourself. The time is going to be 6h over beta to the 1/3 power. Okay? Now, we want the speed when it hits the ground, which is given by the absolute value of the velocity. And the velocity is always going to be positive based upon how we have it defined, as long as we're looking at times before the rocket hits the ground, or at least right before. Okay? And so all we do now is take our velocity function, which is given by 1/2 beta t squared, which means we can plug in any time we want, 1 second, 2 seconds, 3 seconds for this t, and this function gives us the velocity at that time. But now we're looking for the velocity when the rocket hits the ground, so we're going to evaluate the velocity function not at any general time t, but at the specific time, capital T, whenever it hits the ground. Okay, so let's go ahead, and now we know this capital T in terms of things that were given in the problem, h and beta, right? So we get 6h over beta raised to the 1/3, and then we're going to square that. And that's the same thing, and please prove this to yourself if you're rusty with algebra. We get the same thing if we take 6h over beta raised to the 2/3 power, because that's how algebra works. Okay, I hope that's clear. And I hope that cleared up a few things. Alright, so once again we talked about why coordinate system choices are totally arbitrary. You choose the origin of the coordinate system and you choose the direction that it's increasing. Coordinate systems are necessary because they help us pin down lengths in problems, right? The distance h would have never been relevant in our problem if we only ever worked with the acceleration and the velocity. However, in order to know how long it took for the rocket to hit the ground, we needed to incorporate that distance h that the rocket traveled, right? And that distance h just ended up being our position function evaluated at the time when it hits the ground, right? Okay. So there's our answer. Problem 10. Please take a second and read that problem. It'd probably take about 15 seconds actually. In this problem, we have two cars starting at the same place, both starting at rest, but with different accelerations. And we want to know whenever these two cars, which start at the same place, but then divert based on their different accelerations, we want to know when they will once again meet. Okay, so let's get rid of this. First thing you do, sketch the problem. We got one car, and it moves. Whoop. We got another car, and it moves in a line too, just with a different acceleration there. Okay? Alright. So, the highlighter just shows that it's going to move over time, or the faded path just shows the path it's going to follow over time. So, we want to know when these two cars are going to meet again. So if we call this car A, we call this car B, it would be good to find the position functions for each of these cars so we can describe their positions over time. It's only when we have this complete knowledge of their positions over time that we will be able to then decide when they will meet, right? So, let's choose a nice coordinate system which runs parallel to both of these cars' paths. We'll call it the x direction, put the increasing x direction in the direction of motion, which is a good rule of thumb to avoid negative sign issues. Okay, and we'll put our origin at the starting point of the car. So x is equal to 0 where they're both starting. Just like in the rocket problem, we put x equal to 0 where it started. That's not always the most convenient thing to do, but in these two problems that we're working on today, I think it's a pretty convenient choice. Okay. So what we want, the location, the x-coordinate of car A at all times, t, and the x-coordinate of car B at all times, t. Okay? Well, what are we given to help us find that? Well, we're given the acceleration of car A as a function of time. It's just a constant. We're given the acceleration of car B as a function of time, and it's a known constant times t squared, alpha times. And remember, if we have the accelerations, that's the best starting point for then finding the velocity functions, which then give us what we want, the position functions. So let's just look at car A. And this is the strategy. When you have two things moving in the same problem, but they're moving with different properties, for example, in this case, different accelerations, we want to have two different position functions tracking their coordinates along this x-axis, okay? And especially if we want to know when they will meet and where they will meet, because this information will tell us exactly that. Okay, so we start with the acceleration. To get the acceleration, we integrate. To get the velocity of car A as a function of time, we integrate. We're not so interested in it. We're interested in the position, xa, where we'll integrate the velocity to get it. First, we need to integrate the acceleration. We're integrating a constant, so we get kt plus the initial velocity. I'm going to put VA here because this is specifically the initial velocity of car A since we're working with car A's acceleration. Okay? This is going to be 0 since car A starts at rest, which is what we're told in the problem. And we'll always be given some information about it. And if we're not given information about it, we can either figure it out. Maybe that's the problem, is to figure out the thing that we're not told about. Okay? So, to get the position function, we integrate the velocity function of car A, integrating kt, and that gives us 1/2 kt squared, plus the initial position of car A, which will depend on your coordinate system. In our coordinate system, car A starts at the origin. So at t equal to 0, the coordinate of car A is 0. So in summary, at any time t, the coordinate, the x-coordinate of car A, is given by taking 1/2 times k times the time squared. So at 1 second, we can plug in 1 for t. Knowing k, we can then calculate the x-coordinate of car A at 1 second, 2 seconds, 3 seconds, or any time after that. So this gives us complete information about where the car will be at any time t. But this is just for car A. We also need car B's motion. So we're going to follow a very similar procedure, and I'm not going to show the steps. I'm going to go through this quickly. Okay? AB is alpha t squared. We integrate AB to get the velocity of car B. So this is for car B now, as a function of time. The initial velocity of car B is the constant of integration for this integration, and it starts at rest, so the initial velocity of car B is 0, and our constant of integration is 0. The position of car B at any time t is given by integrating the velocity function. That should be cubed. And integrating this gives us 1/12 alpha t to the 4th plus the initial position of car B. Car B starts at the origin along with car A. So we get that constant of integration being 0. Now we know the coordinate of car B. At any time t, we can plug in t equal to 5 seconds, for example, and then we just multiply it by this given alpha, after taking it to the 4th power, of course, divide by 12, and that gives us the position of the x-coordinate of car B at any time. At 5 seconds in that case, but in general we have it at any time now. So in summary, we have found xa, the coordinate of car A at any time, and the coordinate of car B at any time. We're interested in knowing when they meet, so let's define t to be the meeting time. Okay. One more fact we need to know to solve this problem. In order for objects to meet, they must be at what? The same position at the same time. Okay. Let's now write that mathematically, so we have a nice mathematical expression. What that says is the x-coordinate of car A, which is tracking exactly where the car A is at any time t. So, if we evaluate car A's coordinate at the meeting time, it must be equal to car B's coordinate at the meeting time. Okay, so we just go back up here. We see that car A's coordinates given by 1/2 kt squared, and car B's coordinates given by 1/12 alpha t to the 4th. And we go ahead and evaluate those functions at the meeting time, which we do not know, but we can certainly put unknowns into our equation. And this is, 1/12 alpha t to the 4th. Okay. Now we just look at this equation, and we see that the only thing that's unknown is capital T, the meeting time. So we can solve for capital T. Let's get rid of the solution that capital T is equal to 0. Why? Why get rid of that solution? Well, at t equal to 0, both of the cars are where they started, right? And that's obviously one time they're going to meet, for sure. But that's not the time we're interested in. We're interested in the time they meet after they've already started moving, okay? Now let's multiply. So we've reduced each side by t squared. So let's now multiply both sides by 12 to get rid of the denominators, and we get 6k is equal to alpha t squared. Solving for t, we get time it takes for them to meet, 6k over alpha to the 1/2 power. That's how long it will take for them to meet. Notice, in order to get that time, all we did was say was in order for objects to meet, they must be at the same place at the same time. In other words, their coordinates must be equal at the meeting time, capital T. The last question is, where will they be whenever they meet? So that's just given by the coordinate of car A evaluated at that time, or the coordinate of car B. So we're going to evaluate both of these at the meeting time and show that they're equal. Remember that this was given, the coordinate at any time t was given as 1/2 beta t squared. We're evaluating it at capital T, the meeting time, so we get 1/2 beta. Capital T is 6k over alpha, so squaring that just gives us 6k over alpha. And therefore we have 6 divided by 2 is 3 beta k over alpha. Okay? We know beta, we know k, and we know alpha. Those were all given values. And actually, no, beta should not be involved. I think I made a mistake. It should be K. Sorry. Should be K. I don't know. I think I was thinking back to problem 7. That fixes everything. There we go. Sorry about that, guys. Alright. So, xb at any time t. Let's double check this so I don't screw it up. It's 1/12 alpha t to the fourth. So this is 1/12 alpha. Capital T to the fourth is going to be 6k over alpha squared. So just looking at the numerical terms, we get 6 squared divided by 12. 36 divided by 12 is 3. Let's look at the k now. We're just going to have a k squared in the end. And how about alpha? We get alpha divided by alpha squared, which is just going to be alpha. They will meet at the coordinate 6k squared over alpha in our coordinate system. Okay. So, in general, when you have a problem with multiple objects moving around with different properties, we split it into 2 problems where we find the position function and velocity functions of each object separately, and then we go ahead, and if we want them to meet, we impose that at some meeting time capital T, which is sometimes unknown, that their coordinates must be equal, right? And this gives us an equation where we can then solve for that meeting time. Hope this video was helpful, and I will see you guys next week in recitation. Bye.